Thank you for coming out today. We have a wonderful session. I'm Dr. Susie. I'm an assistant professor at the University of Louisville in the Bioengineering department. I'm happy to moderate today. And our first speaker is going to be Jacob Krabs from St. Louis University, and he's going to present his talk on analysis of novel bioreactor design for ultrasound stimulation of cell-seeded cells.
So I'm Jacob, a master's student at St. Louis University, and this is my talk on novel bioreactor design for ultrasound stimulation of cell-seeded scaffolds. So cells respond to a variety of signals, including chemical, electromagnetic, and in our case, mechanical. It has been shown that direct application of low-intensity pulsed ultrasound can have a positive effect on bone fracture repair, where an ultrasound transducer is placed on the skin right above the fracture callus, and then it delivers a very low amplitude pressure to the cells in the fracture callus, which they then respond to via intracellular signaling pathways, and this has a positive role in bone repair. So a way to study this in vitro, since the exact cellular mechanisms are unknown, is through well-controlled ultrasound bioreactors. Here's an example of one such configuration of an ultrasound bioreactor, where there's an ultrasound transducer placed beneath a tissue culture dish where cells are adhered to the bottom of it, and the ultrasound transducer sends out ultrasound waves that stimulate the cells. A couple problems with a lot of ultrasound bioreactor configurations, one of which is that almost all configurations contain at least one air interface, which in this picture would be at the top of the culture medium. When there's an air interface, complete wave reflection happens at the interface, and then the reflected signal interferes with the incoming signal, and you can't tell what exact signal is stimulating the cells and what the cells are actually responding to. Another problem is that these experiments are normally done on 2D cell monolayers, which is not completely representative of the body or the environment in the fracture callus. And so new bioreactors need to be designed to contain a cell-seeded scaffold and eliminate their interfaces. Also, when you put a cell-seeded scaffold in this configuration, one such scaffold we use would be an electrospin scaffold, and those don't stay still in this configuration. They tend to move around and then would be stimulated by different signals throughout the process. So our first objective was to develop a new bioreactor configuration without any air interfaces that also held cell-seeded scaffolds in a stationary manner in the center of the ultrasound wave propagation pathway. And then also to analyze the effects of varying fluid layer thicknesses in the new configuration, which would be the thickness of the water layer and the thickness of the culture medium layer, and also determine the pressure variation over a volumetric average to be representative of a scaffold, as opposed to just taking a spatial average of the dish surface, which is what previous studies have done. And this is all just done through computational modeling. So this was the transition to the new bioreactor configuration. Here's the normal, just ultrasound transducer from below configuration with a tissue culture dish above it. And we wanted to design a new sample holder that comes in two pieces that screw together. And when they screw together, it pushes the air out of the way of the ultrasound waves, so that they can't cause reflection, and there's no air interface. And then at the top of the sample holder is an acoustic absorbent material that absorbs any acoustic waves coming out the top to prevent them from reflecting at the air at the top. So the sample holder was designed in Autodesk Inventor 2018 and then printed using stereolithography using a Form 2 3D printer from Formlabs. The material chosen was clear resin, so that when assembled you can still see inside and see that the scaffold is in the center, as well as there being no air bubbles in the pathway of the ultrasound wave propagation. Also, that picture, the two pictures at the top, that's the CAD model. It shows there was an inner well where we're going to place a scaffold so that it would stay still in that well. Yeah, and then A finite element model was made in COMSOL, and hydrophone testing was done to determine the material properties needed for that finite element model. So an important part of the model was the ultrasound transducer itself. Previous studies have just picked a point and said waves are coming from this point, which is not very accurate at all. And so we modeled the ultrasound transducer with 4 different parts: a matching layer that reduces the impedance mismatch between the piezoelectric disc and the water. Then the piezoelectric disc itself, a backing layer to absorb any ultrasound waves traveling in that direction, and steel casing. And this is the equation used to model the piezoelectric effect of that disc, relating the stress to the electric potential and the displacement to the strain in the electric potential. And an electric potential of 20 volts was applied to the top surface of the piezoelectric disc in contact with the matching layer, and then a ground node was applied to the other surface. Then 3 physics modules were implemented. One was the electrostatics interface that was used to model the electric field displacement in the piezoelectric disc. The other one was the solid mechanics module that was used to model all solid components in this model, which would be the transducer components, the sample holder, and the acoustic absorbent material. And then the pressure acoustics interface that was used to model all the fluids in the model that would include the water and the culture medium. That was just the Helmholtz equation. The solid mechanics module was a simplified version of Hooke's law. So the very first thing we varied was the thickness of the water layer, as shown. And at a position of maximum constructive interference among all of the interfaces, that is what we refer to as an antinode. This is a heat map just showing the pressure field in the inner well, and the pressure is normalized to the maximum value in the culture medium. And then when the thickness of the water layer was decreased by just 0.24 millimeters, it went to a node position, or a position of maximum destructive interference. As you can see, the pressure field was still had the same pattern, just the values were much lower. And this discrepancy between antinode and node was due to a roughly 34% wave reflection at each liquid sample holder interface, just from impedance mismatches. So there's still reflections and interference going on, but a lot less than with air, which would have a 100% reflection. Then, since we're operating in the near field of ultrasound wave propagation, where the ultrasound is very variable in the z direction, we decided to do this simulation in different regions of water layer thickness, from 2 to 4 millimeters, from 24 to 26 millimeters, 49 to 51, 74 to 76. And as you can see, the pattern still looked roughly the same. The antinode to node ratio slightly decreased as we increased the water layer thickness, but overall it stayed around 2. And the average value in these distributions also increased steadily. But yeah, in each graph, these values are normalized to the average antinode pressure in the 2 to 4 millimeter range. Then we varied the thickness of the culture medium layer while keeping all other parameters constant. The thickness of the water layer was set to an antinode location. And for this one, there was a 36% drop in pressure from antinode to node, so it wasn't as big of an effect as the water layer thickness. This is just a radial graph of the radial pressure in the inner well. This showed that there was a potential design flaw in having the radius of the inner well so small, because it caused a very high pressure in the center and then much lower pressures out at the edge, which is not ideal for stimulating a scaffold, we would want the pressure to be constant throughout the whole radius. Then for averaging the pressure over volume, we chose two thicknesses, a 2 millimeter thickness to represent relatively thicker scaffolds, which would be like cryogels or hydrogels that we have in the lab, and then a thinner thickness of 0.2 millimeters that would represent an electrospun scaffold. And so volume average pressure of the antinode is 15% lower for the 2 millimeter thickness. And then we also ran a simulation to vary the thickness from 0.2 to 3 millimeters. And before the thickness exceeded 0.5 millimeters, it changed 14% from 0.2 to 0.5. And after that, the change in average acoustic pressure relative to volume thickness was minimal, less than 2%. And we conducted a time-dependent simulation over one entire pulse. The standard LIPUS protocol for stimulating fracture callus is a 20% duty cycle, as the signal shows. So 200 microseconds of ultrasound followed by an 800 microsecond resting period. And did this for both of the volume thicknesses. And the plateau value in the 2 millimeter thickness was 11% lower. As you can see, it very quickly, within 45 microseconds, reached a plateau value, and then as soon as the active period ended at 200 microseconds, the pressure rapidly dropped off. The values in this graph are averaged over each sine wave, and so as the graph off to the right shows, the plateau value is still sinusoidal, just the average shown in this first graph is averaged over each sine wave. And to confirm that the irregular radial pressure pattern we saw earlier was based on the radius of the inner well, we varied that radius from 7.5 millimeters to 15 millimeters, and these pressures are normalized to the maximum value in the first one with the 7.5 radius. And as you can see, the pressure field gradually stabilized. The lines got much more flat in 15 millimeter radius. The pressure was much lower, which isn't a concern, and they were much less radially variable. And here are some graphs showing that, what those heat maps just showed. The 7.5 millimeter radius, it dropped as low as 5% of the maximum at these 2 points here and here. And then as we went to 15 millimeter radius, they stabilized a lot more. Pressures were an average of 70% of the maximum in the 15 millimeter radius, whereas in the 7.5 millimeter radius, they stabilized to around 38% of the maximum. And yeah, at a radial position of 7.5 millimeters, it decreased by 64%, whereas with 15 millimeters, they only decreased at the very edge by 30%. So in summary, we designed a new bioreactor that eliminated air-liquid boundaries and reduced reflections, which allows for much more controlled experiments where there's much less experiment-to-experiment variability. The water layer thickness variation, which would be the only thing in this configuration really that would be variable, only caused a twofold change in pressure from antinode to node, which is much lower than previous studies have shown. And thickness of the analyzed volume didn't have a significant effect on volume average pressure, which is good. That means that most likely the thickness of the scaffold won't have an effect on the delivered pressure to the cells. And we also found there's a potential design flaw for the selection of the inner well radius, caused significant radial variation in the pressure field within the well. So future work would include actually including a 3D porous scaffold in the model actually including the material properties for the scaffold, and also developing a better method for holding the scaffolds in the dish in a stationary manner without having an interwell that causes a radially variable pressure field. And then also actually conducting ultrasound experiments with cell-seated scaffolds in this bioreactor. Any questions?
You had pressure variations based on radius, based on nodes and true nodes. Do you have any data from previous studies? I know you haven't conducted the studies yourself, but do you have any data from previous studies that shows the variation, either along the radius or due to reflection or something, affecting cells from one zone to the next? Because yes, you showed these pressure variations, but do you have any data from previous studies that would validate your results?
From one zone to the next, what do you mean by that?
Because you have these pressure variations, right?
Mm-hmm.
And so if you look at it, for example, whether it's a 15 millimeter plate or a 7.5 millimeter plate, at the center you had this spike.
Yeah.
So the cells at the center should be different
Yeah.
after subjecting them to somewhere where you would expect a lower pressure.
Mm-hmm.
Do you have any preliminary data that actually shows that?
Shows that the cells respond differently, and that, no, we do not. We just, in general, want to stimulate all of the cells at the same pressure, so we just want to avoid that. Probably.
And you also had like a 2 millimeter thickness for your, and you mentioned hydrogels. How do you get the nutrition down to the cells? Because if you have a 2 millimeter thickness, it's diffusion limited, right? Especially with the hydrogel.
We haven't tried out hydrogels yet. I was mainly referring to cryogels. That's what we've tried out mostly. That they're macroporous and the media very easily goes into those.
Follow up on that real quick. Was there a reason in your design you started at, I think, 7.5 millimeter radius, and you obviously increased to get rid of that peak in distribution and pressures, but is there a reason you started small, or is there an ideal size for you in terms of your bioreactor that you're looking for?
The 7.5 radius was, I did this bioreactor for my senior design, and at the time I was just told that the scaffolds were one size and then they were a different size, and I tried to make it close to that size they fit in.
Thank you. Our next presenter is Kamal Amuda. Sorry. He's going to present on MRI markers for early assessment of blood cancer. A review.
Hello everybody. I'm gonna talk about MRI markers for early assessments of bladder cancer. It's a survey presented by Kamal Hamuda, PhD student. Medication bladder cancer numbers. In UCA, bladder cancer is the seventh most common cancer with almost 73,000. This image shows the top 10 cancer by rates. The first one is female breast, second one is prostate, and the seventh is urinary bladder. Almost 20 new bladder cancer cases were reported for every 1 million people. Bladder cancer is fourth most common in men and 11th most common in women. There are about 16,870 deaths in 2017 for bladder cancer in USA. The first question is, what is urinary bladder? Urinary bladder is a part of urinary system. This is a urinary system, and this is bladder. This image show schematic illustrations of the bladder, which bladder wall consists of two main parts, mucosal layer and muscle layer. Another question is, what is bladder cancer? Tumors or cancer can be either localized internally in the bladder, it's called intravesical, or extended across the bladder wall. Tumor with a high stage invades nearby organ such as prostate or invades pelvic wall. There are 4 types to extract diagnostic markers. For bladder cancer patients. The first one is clinical markers, and the second one is imaging markers, for example, DCE, MRI, or DWMRI. Third one is genomic, DNA, RNA, and third one is histopathology. Imaging marker will be illustrated in more details in these presentations. Objective diagnosis of bladder cancer depends on 4 major factors. Bladder cancer staging, related to the position of cancer inside bladder, is classified into 8 stages. Lymph node metastasis, it's related to position and the number of lymph nodes. It's classified into 4 types. N0, no lymph nodes. N1, it's single lymph nodes and the position in the true pelvis. N2 is multiple lymph nodes and the position also in true pelvis. N3 is metastasis, is in common iliac metastasis. Distant metastasis, if the lymph nodes make metastasis into another organ or not. It's classified into 2 types. M0, no distant metastasis. M1, there is a distant metastasis. And the last one is bladder cancer grading. Assess aggressiveness of bladder cancer. It's classified into 4 types. First one is urothelial papilloma, and G1 is low grade, G2 is moderate, and G3 is high grade. Bladder cancer staging will be illustrated in more details in the next slides. This image shows schematic illustration of bladder with staging. This TS, TA, T1, T2A until T4P. These stages are classified widely into 2 main types. Non-muscle invasive bladder cancer, the staging is less than or equal to T1. It represents about 75%, and non-muscle and muscle invasive bladder cancer, it's staging greater than or equal T2A. This it represents about 25%. By the time from 20 to 30% of non-muscle invasive bladder cancer advances to muscle invasive bladder cancer. Diagnosis of bladder cancer. The main role of using medical imaging to help physician to more accurately localize and diagnose bladder cancer and therefore select appropriate treatments. MRI is the best among all modalities for malignancies and lymph node staging because MR deals with soft tissue with avoiding exposure to ionizing radiation. Multiparametrics MRI are recently explored for three types. First one is enhance the accuracy of diagnosis. Second, monitoring the response of bladder cancer patients to chemotherapy. The third is detection local bladder cancer recurrence. Multiparametrics are used individual or a combination of them, functional or anatomical. There are two types of MRI-based analysis methods. First is based on radiologist to other expert assessment commercial soft package. Second focuses on development of computational CAD system. The first one is expert-based assessment methods based on radiologists or other expert assessment using commercial soft package. MRI images can be divided into functional image and anatomical image, and functional image can be divided into three types: DW-MRI, DC-EMRI, LME-MRI. There are many markers is extracted from functional images, which appearance diffusion coefficient is extracted from DW-MRI. Wash in and wash out is extracted from DC-EMRI, and visual assessments is performed to LNE-MRI. An anatomical image is divided into two 1 and 2 MRI, which two important markers, volume and this, are extracted from T1 and T2 WMRI. All these markers help to do bladder cancer diagnosis. This table shows the recent MR studies of assessments of bladder cancer. MRI, it can be divided into are used individual, for example, functional or anatomical, or a combination of them, or a combination of function, or a combination or anatomical and function. The users and results are shown in all for every types. I will focus on three results because which give a high result as the highest result. The combination, the first one is T2W-MRI and DW-MRI, determines the staging. DW-MRI and LNE-MRI differentiate between benign and lymph node metastasis. And the last one, DW-MRI and DC-EMRI, assess aggressiveness of bladder cancer, which give the highest value in the results. The second one for MRI based analysis method is computational based CAD system. CAD system for bladder cancer detection and diagnosis are mainly introduced to decrease the interpretations time and read fatigue to the physician. There are three basic steps for CAD system for bladder cancer. First, segment of the inner and the outer boundaries of the bladder wall. Second, picture features extraction that show significant difference between carcinomatous tissue and bladder wall. The last one is classification. Top the selected feature are fed to machine learning classifier. For example, support vector machine to distinguish between diseased and healthy tissue. Discussion. Multiparametric MRI has found to be useful for bladder cancer. 4 factors. Number one, bladder cancer staging is the best combination up to date is T2W, MRI, and DW MRI. The second, lymph node metastasis. Fusion between DW MRI and LND MRI increase the detections of lymph nodes. Bladder cancer grading, the combinations of DW MRI and DC EMRI enhance bladder cancer aggressiveness accuracy. The study has some limitations. The use of DCMRI is not always recommended, especially for patients with kidney problems. Individual MRI scans, for example, DW, has low sensitivity and specificity for bladder cancer diagnosis, if not combined with another modality. The main role of using medical aids is to help physicians to more accurately localize and diagnose of bladder cancer and therefore select appropriate treatments. The treatments option is widely classified into non-muscle invasive bladder cancer and muscle invasive bladder cancer. And muscle invasive is divided into metastasis and non-metastasis. There are various methods for the treatment inside these two categories. Depends on the value of 4 factors: T, N, M, and G. Future word, new research path is design CAD system with high accuracy, identify chemo-resistant patient by extracting markers for patient response to chemotherapy using genomic data, MRI modalities, and pathological data. Thanks.
So nice review, and you mentioned in your future work that you're looking to design a CAD system with high accuracy. Can you comment on how you're planning to accomplish that? Is that your second point, and what about sensitivity and specificity?
Second point for future work?
Yeah.
Identify chemotherapy?
No, so you said you would design a CAD system with high accuracy. How?
And one point was CAD system for what? Because there is CAD system to detect bladder cancer, or CAD system to see the resistance of the bladder cancer to chemotherapy.
CAD system we use it for diagnosis the bladder cancer, to interpret the chemo-resistant patients, predict for the patient who will resist for the chemotherapy or not. CAD system.
No, so in this case, he wanna design a CAD system not to diagnose bladder cancer, a CAD system to predict the resistance of chemotherapy to the resistance of bladder cancer to chemotherapy. So in this case, we can either to recommend chemotherapy to the patient or not.
The second point is.
So that's why, when you said CAD systems, computer diagnosis, right? So it didn't make sense. So that's what I was saying.
Almost the same. Thanks.
Okay, our next presenter is Islam Rita, computer-aided system for prostate cancer diagnosis.
Good morning. I'll present our work on developing a computer-aided system for diagnosing prostate cancer. First, I will begin with the research motivation. According to the recent statistics, prostate cancer is the most common cancer among American men and the second leading cause of cancer death after lung cancer. 1 in 7 men will be diagnosed with prostate cancer during their lifetime. In 2018, the number of American men that will be diagnosed with prostate cancer will exceed 164,000, and the number of people who will die will exceed 29,000. The good news is that early diagnosis of prostate cancer can result in reduction of this mortality rate. This because this enables the physicians to early to early treat the cancer before it develops to a clinically significant stage. Currently, the current techniques for diagnosing prostate cancer include of two initial techniques, in addition to the gold standard, which is biopsy. The first initial techniques for diagnosing prostate cancer is digital rectal exam. In this techniques, a physician manually checks the prostate through the rectum for any abnormalities. The limitation of these techniques is that it is a highly invasive techniques. Also, its accuracy depends on the physician experience. And the last drawback of this technique is that only sufficiently large tumors can be detected using these techniques. The second initial technique for diagnosing prostate cancer is prostate-specific antigen screening. This is a blood test that measures the concentration of the BSA in the blood, because it was shown that elevated BSA levels in the blood can used as indicator for the presence of prostate cancer. The limitation or the drawback of this technique is that it has a high risk of overdiagnosis or high false positive rates, because elevated BSA levels can be due to other conditions such as enlarged or inflamed prostates. Due to the limitation of these two techniques, they are only used as indicators for the presence of prostate cancer and determines who should undergo the biopsy, which is the gold standard. Also, biopsy is the gold standard, but it has its own limitations due to its invasive nature and high cost. Also, about 30% of cancers of clinically significant prostate cancer can be missed by biopsy, because due to the blind nature of tissue sample acquiring. Also, biopsy has more complications, so like bleeding and infections. Due to these limitations, therefore, there is an urgent need for a non-invasive technique for diagnosing prostate cancer, and this is the objective of our work. In this work, we are trying to develop an image-based, non-invasive, computer-aided system for diagnosing prostate cancer from diffusion-weighted MRI data. The most common MRI modalities used for diagnosing prostate cancer are T2-weighted MRI, dynamic contrast enhanced MRI, and diffusion-weighted MRI. Diffusion-weighted MRI has multiple advantages. First, diffusion-weighted MRI, as I said, has multiple advantages. The first advantage of diffusion-weighted MRI is that it does not involve the use of any contrast agents, which makes it appropriate for all kinds of patients. Also, second advantage for diffusion-weighted MRI is that it can be acquired very quickly. It was shown that 1 point imaging the entire prostate takes about 1 minute and a half at multiple p-values with 1.5 Tesla scanner. This time also can be reduced if we use parallel imaging systems. This figure shows the framework and the pipeline of our proposed framework and its basic processing steps. There are 3 basic processing steps, which is prostate segmentation, then picture extraction, and the third stage will be the classification. The input to our system are diffusion-weighted MRI data acquired at 7 different p-values. The following slides will explain these steps in more details. Our system was evaluated using diffusion-weighted MRI data sets acquired from 40 patients. 20 of them are benign and 20 are malignant. This diagnosis was based on biopsy. Also diffusion-weighted MRI data were acquired at 7 different p-values. And also they were acquired using 2 different scanners with 2 different magnetic field strengths, 1.5 Tesla and 3 Tesla. This images here shows a cross-sectional of prostate at different p-values, B0, B100, and B700. The first step of diagnosing prostate cancer is prostate segmentation, which is this step. Prostate segmentation the purpose of this step is to define the region of interest and apply the following processing step on that region of interest. Prostate segmentation have multiple challenges. The first challenge, if it is applied manually, it will be tedious and time consuming. And the second challenge for prostate segmentation from MRI is that prostate appearance patterns of prostate regions and the prostate shapes vary across subjects and within each subject, and this leads to intra and inter-observer variability. In our system, we choose to replace the complicated and accurate prostate segmentation simply by selecting a region of interest. This region of interest will be a square window of size 70 pixels from the center of the diffusion weighted MRI image. This window will contain the prostate tissues in addition to the surrounding other surrounding tissues. And the following processing steps will be applied on that region. The second step of our CAD system or computer-aided system is feature extraction. In this step, we are trying to extract discriminatory features that has ability to differentiate between benign and malignant prostates. In our work, aberrant diffusion coefficient is used as the discriminatory feature. Aberrant diffusion coefficient is a measure to the impedance of diffusion within of water molecules within the tissues. Aberrant diffusion coefficient was chosen as a discriminatory feature because it was shown that malignant prostates have, or malignant tissues have a lower average ADC values than benign or healthy tissues. In order to calculate the ADC maps, we need two images. The first image is acquired at a given p-value. In this case, we call it BI. And the second image is the baseline, or an image acquired without diffusion, which is B0. And it is the ADC is mathematically defined using this equation, where G sub I is and G0 are the image signals at a given p-value and B0. When we calculate we apply this equation on every pixel, the result is called ADC map. This ADC map will be the input for the for the final stage of our CAD system, which is classification. Also, these ADC maps at the different p-values, at the 7 different p-values, will be normalized and refined to remove any inconsistency. The last step of our CAD system is diagnosis. The purpose of this step is to classify the prostate case into either benign or malignant. The classification was performed through, or the diagnosis was performed through a classification system of 2 stages. The first stage uses 7 different convolutional neural networks, 1 for each p-value, as shown in this figure. The input to the convolutional neural networks will be the defined ADC volume calculated in the second step, and the CNN, every CNN at each p-value will produce 2 output probabilities, or what the probability to be benign and the probability to be malignant for each case at each p-value. These probabilities will be integrated and used as input to the second stage of classification, which employs support vector machine with Gaussian kernel to get the final diagnosis. In our work, we choose to use convolutional neural networks because there are multiple advantages for using convolutional neural networks. The first advantage is that convolutional neural networks have multiple layers than traditional neural networks. These multiple layers allow the network to learn high levels of abstractions that result in better predictions. Also, convolutional neural networks, the input to it can be image. In case of traditional neural networks, the input must be a vector. If we transform the input image into a vector to be used for a traditional neural network, this results in losing spatial information, which affects the accuracy of a traditional neural network. So this is why we choose to use convolutional neural networks in our work. Regarding the results of our work, the EDC maps or volumes for the 40 subjects were used to train and evaluate the accuracy of the different CNNs at the different V values using a leave one subject out scenario. This table shows the resulting accuracy at the different V values. According to the values in this table, the accuracy need to be improved, especially in terms of the specificity. This indicates the importance of the second stage of classification. And this table 2, shows the results of the second stage of classification for the proposed support vector machine with Gaussian kernel and 3 other classifiers. The results here show that the proposed model that uses support vector machine with Gaussian kernel got the best or the highest results. In conclusion, this work represents a non-invasive image-based computer-aided system for diagnosing prostate cancer. The accuracy of the system improves by integrating the different B values in the second stage. Our future work will focus on using the proposed system in a clinical trial to measure its robustness and limitations on a large clinical data. Thank you very much.
Do you expect the algorithm you're using to be able to distinguish between a prostate with cancer versus one that just has an infection based on the parameters that you're evaluating?
Yes. In this case, because the values, the ADC values, in case of malignant prostates, are much lower than even in hyperplasia or in larger prostate. So it can have the ability to differentiate between both of them. Because the feature that we are using, have a good separation between these cases. Either healthy and benign or malignant in the other case.
Well, have you taken MRI images of not necessarily a healthy prostate, but a prostate with no tumor? Because you mentioned, I think, 20 benign and 20 malignant. Have you taken some images of no tumor to see?
Some of these 20 that are benign are, I think we have 1 or 2 cases that are healthy without any tumors.
You mentioned a 95%. I saw 95% a lot. That means you got 1 out of 20 wrong, right? So
yes.
Of the 20 that you had.
Yeah.
So,
but this after the second stage of classification. Yes.
And so, why do you think you got that one wrong, or what was confounding about it that you got it wrong? And second is, how do you, when you have a small sample, how do you separate your test population? How many did you test it on? How many did you validate, or did you use a LOSO method for testing and validation?
For addition, we use leave one subject out.
Okay.
20, 35, 39 will be training, and the last one will be testing, and this was repeated. And regarding the case with that is misclassified, most of the time it's the first case, because the network need to be time or need many iterations to be trained, and in the first stage, this sometimes it's not trained well. So this is the result that the first subject most of the time got the misclassification. Any other question? Thank you.
Our next speaker is Ahmed Shafi. He's going to present on the integration of CT-derived features for accurate detection of lung cancer.
morning. My name is Ahmed Shafai. I will introduce our work on the integration of CT drive feature for accurate detection of lung cancer. Lung cancer is the second most common cancer in men after prostate cancer and in women after breast cancer. But it is considered the leading cause of cancer deaths among both gender, as the number of people that die every year from lung cancer is more than the number of people that die from prostate cancer and breast cancer combined together, as 1 out of every 4 cancer deaths is resulting from lung cancer. Histological examination through biopsies is considered the gold standard for final diagnosis of pulmonary nodules. Even though resection of pulmonary nodule is the ideal and the most reliable way for diagnosis, but there is a real need to eliminate the risk associated with this surgical procedure through a non-invasive way. And actually this was our great motive to implement our non-invasive CAD system. So we can say that our objective mainly are 2 things. The first thing is to implement our framework, which is non-invasive, to classify the nodule whether it is malignant or benign, then to evaluate our system accuracy based on a confirmed radiologist diagnosis for this nodule. And actually we use LIDC database, which contain more than 700 nodules to detect, to evaluate our accuracy. This is our framework. Actually we can divide it to 2 main parts. The first one, which is appearance based. The second 2 module, which is shape based. The input for our framework is CT scans in 2 ways. The first one is a grayscale for this nodule, and it's binary mask, which is in black and white. I will start to talk about each component separately now. The first component is the MGRF. The spatial distribution of the Helms field value vary between benign nodule to malignant nodule. So we try to describe this texture appearance by developing a new higher 7th order Markov-Gibbs random field to describe the texture appearance of the pulmonary nodules. And we use this model to calculate the Gibbs energy for every voxel in the volume. And actually this give a good discrimination feature between malignant and benign, as the high potential of malignancy is indicated by lower energy. This is actually 2 examples of malignant nodule and benign one. The difference in the appearance is clear here, but to make it more clearer, we can check the 3D visualization of the Helms field value for each one of them. We can find this one is homogeneous. This is why it looks like smooth one. But for this one, because there is a difference in the grayscale, it looks like sparks here. It is not homogeneous, as you see here. When we learn our model, depending on the benign nodules, and we calculate the Gibbs energy, you can see that the malignant one have lower energy than the benign one. The benign one have a higher energy. This is why we claim that it gives a really good discrimination feature between benign nodule and malignant one. The second feature is local binary pattern or adjustable local binary pattern. Actually, local binary pattern give a good description for the texture in general and involves the spatial distribution of the neighbors voxels. But when we try to implement this or to try to this descriptor in our application in pulmonary nodule, we face mainly 2 problems. The first one, that the benign nodule have a homogeneous texture, and this make a problem when a small noise happen to this one, because it make the descriptor to assign 0 for some of them and 1 for some of them, although they should have the same value. To be more clear, let's see this example. Let's see this is the texture. All of the voxels have value of 200. When we try to use the LP descriptor, it will assign all values for this to 1. Actually, it compares these values with the center. If it is greater than or equal to B1, else it will be 0. Let's imagine that a little noise happened or a tiny noise happened for these values, and it becomes like this. The 200 become 199, this 200 become 198, this 200 become 202. Although it is the same thing, just a small noise, the feature will vary and will look like this. All these ones converted to 0. So we have different feature or different descriptor for the same nodule. And this is the first problem. The second problem that it will not be able to distinguish between two voxels if both of them are greater than the center voxel. In other words, if one a little bit higher, like this 152 and this is 150, this is two higher, but this one is 300, is doubled. So both of them will have the same value and we will miss the difference between both of them. So to solve this problem or to overcome these problems, in order to not check just this value with the center value and check the difference if it is greater than 0, it will become 1, else it becomes 0, we decide to use a threshold. This threshold T will solve both problems we faced before. But the problem now is how to set this threshold. The first thing is to set it as a constant value, and it will cause a big problem. It is not reasonable because the difference here is 15, the difference here is 15, but this one is doubled. So we wanted to check what is the noticeable change that we could use for this threshold. And this is why we called it is adjustable LBB, because this threshold will depend on this value. Actually, this law is called Weber's law, or Weber's, which depends on Weber fraction, as a noticeable change is proportional constantly with the origin value. So we'll change this, and this is actually how we work now. This is the input, grayscale, and this is how we imagine the values in this one. Then we started to doing the threshold using the new equations. This threshold is just C multiplied by K. The C is the center value, which is 50 here, and K is a Weber fraction, which we try different one, and you can see this in the paper, and the best one that gives the best result was K equal 0.08. After thresholding, this is the values we have. Then we start to multiply these values with the weights to have our binary pattern, which looks like this. The problem that this binary pattern we have is not rotation invariant. To solve this problem, we try the different rotations combinations, and after that we select the lowest binary number or the lowest code to be the code for this one. And we use this code as the output feature for this local binary pattern features. Next, I will talk about the shape-based features. I will start with the spherical harmonics one. Spherical harmonic expansion is used to describe the shape complexity, and we describe this shape complexity in terms of reconstruction error curve. The potential of malignancy is indicated by higher shape complexity. This is actually how we works. We have just a binary mask for our nodule. Then we start to generate our 3D volume for this nodule. Then we started to make a deformation for this one on a unit sphere. Then we start to reconstruct this shape using different order of spherical harmonics from 1 to 70. After we have all this one, we start to build our reconstruction error curve, which describes the value of error. You can see here that the error decay. Every time we have more orders, the value of error starts to decay. And actually, these are our output features for this module. This slide showed two nodules, one benign, one is malignant. Just I want to show you how it is. The error here in the benign one decays so fast because the shape is not that complex. But in the malignant one, because it has complex shape, it needs more than spherical harmonics to be introduced or to be generated again with small error. The last part, which is a basic feature, a basic geometric feature, we select a set of 7 features as the characteristic of the nodules vary from benign to malignant, and these features already varies. And just simple features like size, extent, solidity, surface area, and we use all these features to be fit. Now, after we finish all these features, it's time to use these features for classification. We use the two-stage classification way. The first one is autoencoder network. We use these two autoencoders for the MGRF and spherical harmonics. Then we have an initial probability output from each one of them, which is chained with the output probability that come from the LPV classification, and we use for this one a support vector machine, which give a better result than the autoencoder here. And because these simple features, there's no need for a neural network, we use just a softmax to have other probability, and we chain all this probability to be fed to the last chain, to the last stage, to have a final probability for our work. We test our data, as I mentioned before, on LIDC database. We select 727 nodules, which is almost balanced, 413 benign and 314 malignant, which come out from 467 patients, and the result was really promising. To have the feeling of the effect of each part of them, we report the resulting depending on each one separately at the beginning. We can find that the accuracy of each of them is greater than 80, but when we fuse all of them, the combined feature was around 92 or 93. We also compared our work with other work from 2015-2008. We can see that we have a superior accuracy over all of these features. Actually, this happened because the first thing, the multiple features that we have, and the way of fusing all of this. To sum up what I mentioned today, we introduced a new non-invasive classification system for lung nodule, whether benign or malignant, and this system consists of mainly 3 steps. The first one is extraction of the appearance features in terms of adjustable local binary pattern and the Gibbs energy, and extraction of shape features, which we can say this in terms of the reconstruction error of spherical harmonics and the basic features that we use, and the final step for the nodule classification using a deep autoencoder network. That's all I have for you today. Thank you.
So it is very good presentation, I like it.
Thank you.
I just, again, I have an idea for adjustable LBB.
Yeah.
What about if we use automatic clustering and to take the segmented nodule and then apply a clustering method to see how many clusters? Then you can use this to determine the binary code instead of using
the binary code or the threshold?
The threshold, yeah, okay, because when you, and in this case you can have more than one class.
Yeah.
And in this case you can avoid the idea of using the threshold, and now you can have a dynamic way to estimate the number of clusters, because one nodule can come with just 2 labels, 0, 1. Maybe another one can become 0, 1, 2. Maybe another third one is especially when you go to ground the glass nodules. You can more than one label. So do you think is this can improve the result?
Yeah, of course. It's a good idea. We can try.
Okay, yeah, because I like the idea, but if we can change this, it can lead to something like that. But overall, very good presentation.
Thank you.
Did you have?
No, you can.
So when you examine the database nodules, are they predefined boundaries for the nodules, or are you defining them?
Actually, I say that I am very lucky in working in this field, in this part in the lung, because the LIDC database have a really good description for everything. Like this is annotated by 4 radiologists, and they make it in 2 stages. The first one is blind one. The second one is unblind. After they know the result from each one, they start to discuss together and give a final diagnosis. And we have a diagnosis for this one. and some features that they come from this radiologist and have real boundary, a good boundaries for this one.
So for yours to work, a radiologist would first have to define the boundaries
Yeah,
of the node?
yeah, this is where we get the binary mask.
Gotcha.
Yeah.
Yeah, kindly could bring the slide for the thresholding function formula where LLD. You mentioned that if G minus
This one?
yeah, this one. How do you conduct that C is always smaller? Because if C is this formula, if it's switched, it will make negative value.
Yeah.
With my point. So how you are you scanning first to get the C value, or how you determine the C in this formula?
The C value is the center value
Yeah.
here in the voxel. In our volume, we select the center value. This center value is our central value when we try to calculate the features.
Okay, but
So I mean here, this is 200. This one, this is 15.
yes.
Yeah.
But if the second formula, if C is bigger,
Yeah.
so the negative just will make big difference, but negative. So the condition will not be satisfied. Because in this situation, C, B minus C will be negative.
Are you familiar with the local binary pattern feature?
You can explain it? if you
Yeah, okay. Local binary pattern, we are trying to compare the value in the center with this value. Actually, this is the original one. If it is greater than the value in center or equal, it becomes 1. This is what this formula says. If it is less than that, it is 1. It is 0. So we are trying to have this threshold in 1 pound. It is not in 2 pound. We can't have the absolute value, and I think this is
Yeah,
what
that's
you
what
mean.
I'm asking about.
Yeah.
You can-
We can do this in something called ternary, local ternary pattern, because they make 3 choices, like 1, -1, 0. So I think it will be a good idea if we are working with a local ternary pattern, not local binary pattern. Local binary pattern will have 1 pound. So we try to have these boundaries or these values through this threshold in one side, not the 2 sides. But it is a good idea if we're using local ternary pattern.
Okay, thank you.
So, for the results you display, you are using k-fold cross-validation or training test split?
We use for k-fold validation, for 4-fold validation.
If there's any other questions, I'm going to ask it for at the end of the session. Thank you for
Thank
that great talk.
Yes, sir.
Okay, our next presenter is Adam Russ.
Royce.
Sorry. Extracting motor imagery features to control 2 robotic hands. Sorry, I'm not sure where you say something.
وكان في قبول بلا منحازة من
Well, hello, I'm Adam Royce. I'm a graduate researcher at Wichita State University, and as introduced, I'll be presenting my research on extracting motor imaginary features to control 2 robotic hands. Oh, there we go. I gotta figure it out, I guess. Here's a brief outline of what I'll be covering today. I'll give some introduction into brain-machine interface and how we acquire the signals which we're using for that. And then I'll discuss our study's goals, followed by the materials and methods used in our research. And then I'll go over our results, finish up with a conclusion, my references, and open it up for questions. So here's a brief introduction. There are currently around 4.5 million Americans living with some form of paralysis, That can be caused from spinal cord injury, multiple sclerosis, any sort of thing that's affecting their spinal cord or nervous system that causes their paralysis. And BMI technology acquires signals from the brain and then detects features from them and generates control signals in real time for a device. Now, there's a distinction between BMI and BCI. BCI is where the device that you're sending the signals to or using to control is something within the computer, so some sort of environment. If you're using an external device, then that would be referred to as BMI. It can be used in rehabilitation, prosthetics, and basically it helps these individuals with the paralysis to be able to regain some of their activities of daily living. And it requires real-time acquisition of the brain signals and conversion into features to be used by the device. So for our studies, we're using non-invasive EEG signals. So for the EEG, you have the different frequency bands. We are focused on the alpha and beta, which are 8 to 12 hertz, and then 12 to 30 hertz. And those are related to, the alpha are related to the initiation of movement and the thoughts of movement, and then the beta are actually the physical movements taking place. So, we use feature extraction to get features for our device, and then our specific type of signal that we're using are a type of sensory motor rhythm called motor imaginary signals, and those come from the motor cortex, sensory motor cortex of the brain. For our signal processing, previous research has used time or frequency based analysis. For ours, we decided to use the Yorth parameters because it combines both the time and frequency domains into one. So, and our goal of the study was to combine the Yorth parameters and use that in combination with a neural network to increase BCI accuracy and speed, and we also plan to try to minimize the number of electrodes used. Here's our EEG system that we used. It's the Guger Technologies 16-channel EEG system, and we used a sampling rate of 512 hertz, and signals were processed using MATLAB Simulink. This was an IRB approved study. We recruited 8 healthy subjects between ages of 18 and 52, and we used a bipolar montage which collected signals from C3 related to right hand movement, C4 related to left hand movement, and then FCZ. And the signals that we were looking to try to acquire for the specific movements were 4 states, which were left hand movement, right hand movement, both hand movement, and then resting state. So for the Yorth parameters, we took the signals and did the separation into alpha and beta frequencies, followed by taking the average of those, and then we used those Yorth parameters, which were activity, mobility, and complexity. The activity is the signal power, mobility is the mean frequency, and complexity is change in the frequency. And for our window with the Yorth parameters, we used 750 samples. Now, other research has used longer samples, and we chose to do our implementation in MATLAB Simulink rather than some other open source software, because those open source softwares use a longer window for collecting those samples. So our window translates to about 4 seconds for our window, whereas the other ones use a window of about 10 seconds. So by minimizing that window, we hope to then speed up communication to whatever device you're going to be using. So here was our neural network. We used a pattern recognition neural network, and we tested out different training algorithms, and we found that the scaled conjugate training algorithm provided the highest accuracy. Now we have our 16 inputs, and those come from the C3 and C4 for the 3 Yorth parameters, and then our mean of each of those signals once we separate those out into alpha and beta. And then we're classifying to those 4 hand states. Now, those hand states that we classified to got sent to 2 robotic hands. We used the U-bionic hand for this, and that required us to use a H-bridge motor driver for that. Here's a video of the recording of the person's signals. We had the left arrow, which told them to move their left hand, right arrow to move the right hand, up arrow for both hands, and then the resting state. Now, we recorded both actual movements and imaginary movements to test and compare which would actually be better for controlling the hands. Now, in the people with the paralysis, they're not able to actually use those actual movements, so we wanted to see what the differences would be with our healthy subjects. Here we have the results of our testing just for the EEG signals acquired. As you can see, the beta waves are higher during the actual movements, as you can see here, and these are both for the left hand. And then the alpha waves are higher during the imaginary movements. As I mentioned earlier, that's what you would expect, and this confirms that we're getting the type of results that we would expect from our neuroscience study, in that our actual movements are seen higher with the beta waves, and our imagined movements are seen higher with the alpha waves. Now here's the results of our network classification. All of these are within the 99%. And then here are the results of our testing of the different training algorithms. So here we have actual movement with the scaled conjugate gradient. This is our imagined movement of the scaled conjugate gradient. And then using the Bayesian regularization. And finally, the Levenberg method. This is a recording of an offline study, which was from taking the individual's recorded signal and then testing our network to show that it was working properly, so that we could then further do testing in real time. And this is a video in real time. So here we have the actual movements. And here we have the imaginary movements. In conclusion, we found that the scaled conjugate gradient showed the best of the different training algorithms that we tested. It showed the lowest number of epochs required to reach the mean squared error. And we also conducted, as I showed you in the previous 2 slides, an offline analysis and an online analysis. And it showed in the offline analysis that our actual movements were showing better results in controlling the hands than our imagined movements. We were able to use 3 electrodes and minimize the number of electrodes used. And our decision to use FCZ rather than CZ was based on previous research. Typically, FCZ is not used when doing this type of configuration, but we found in another study that they were able to show good results with using FCZ, and we wanted to confirm their results. In our future works, we plan to investigate how to further speed up the BCI communication, and we also plan to test different transfer functions within our neural network to try to get higher accuracy and better control of our devices. These are my references. Thank you for your time. And are there
So for the neural network, how the data was divided into train and test splits here? Or they leave one out, or just you divided the 10 subjects
We just divided the 10 subjects.
to 50%? So the training amount to how many subjects?
So each of the subjects got their own training.
Each of the subjects got around training.
Yeah.
So it was a leave one out.
Leave one out.
You just
K-fold. K-fold. It's K-fold, right?
is it k-fold or leave? How did you divide them into to feed the training then the testing? How they were divided?
So we used each individual's inputs into the networks and then trained it off of that, off of their signals, and then found the classification off of their
So
signals.
the reported accuracies are for the training error, not the testing error, right?
Correct.
So that's why they are all near 100%.
Correct.
So didn't you think that you need to add some drop-off or something just to prevent the overfitting of the model?
Yes.
Because this model might be real error of 0% or 100% accuracy, or it might be an overfitted model for the training error. Did you try to solve this problem, or this will be in the future?
That'll be in the future.
Okay, thank you very much.
Thank you. Our next presenter is Yasser El-Nakib. He's going to present on towards accurate personalization of autism diagnosis using different imaging modalities, SMRI, fMRI, and DTI. You know how to use the laser pointer. This one? You know how to use the laser pointer?
Good morning, everyone. I'm Yasser El-Nakib, and in this talk I am going to present our teamwork towards an accurate personalized diagnosis for autism using structural MRI, functional MRI, and diffusion tensor imaging. So the medical problem we are trying to diagnose in this work is autism. But first, what is autism? In short, autism is a mental disorder that affects communication, the ability to communicate and interact with other people, and form relationships. It's present from early childhood, and its most prominent effect of it is more linguistic, behavioral, and social skills. Sorry. And according to the American Center for the Disease Control and Prevention, 1 in each 59 children in the US are diagnosed with autism. 30% of these children may develop epilepsy at later stages. Although what causes autism is yet unknown, it's mainly believed that genetic and environmental factors in some complex combination are responsible for developing autism. Currently, most of the methods are subjective. It's based on the pediatrician's report, and if a patient is fine symptomatic, he needs more meetings with the physician until he gets an accurate diagnosis. So this takes a long time, and it's not applicable at very early stage. And so there is an urgent need for a non-invasive technology that's automated and non-subjective for diagnosis of autism. And most of ongoing research can be split into neuroimaging based, or genomic based, or behavioral based, and our work can be in the field of neuroimaging research. Most brain imaging technology for diagnosis are structural MRI, or DTI, or fMRI, and we are gonna, in this work, we are gonna explore both SMRI, DTI, and fMRI in order to integrate the anatomical from structural MRI and white matter from DTI and functional connectivities from fMRI in order to get an accurate diagnosis for autism. This is our diagnostic pipeline. It has like 3 main frameworks. One based on based on the structural MRI data, and one based on the functional MRI time course data, and one for the diffusion tensor data. In the next slide, we are gonna go through each of these frameworks, and there is a global fusion stage in which we aim to fuse all these classification. In order to get a final global diagnosis. So the first is the diffusion tensor imaging. Diffusion tensor imaging is the first, it gives us a window on the white matter connectivity inside the brain. It gives a measurement of the diffusion of water molecules using MRI gradients. So we have some 6 or more gradients applied on the brain, and from them we can get the diffusion tensor at each voxel. Analyzing this diffusion tensor and solving for eigenvalues and eigenvectors, we can get the magnitude and direction at each voxel inside the brain. So this can provide us tractography, a 3D construction for the white matter pathways inside the brain, as in this figure. And of course, if the eigenvalues are all similar, we have like spherical diffusion. It means that there is no diffusion in this voxel. If there are a dominant diffusion direction in this voxel, we have a more high anisotropy in this voxel and high diffusion in some direction. And the pipeline for the diffusion tensor imaging part is we get the diffusion weighted MRI data. We have variable processing steps using FSL for brain extraction, for motion correction, and for getting the diffusion tensor volumes. After we get the diffusion tensor volumes, we extract the feature we are going to work on. So we have 5 features here: the eigenvalues itself, and the mean diffusivity and functional anisotropy. Then we map this feature on Johns Hopkins Atlas to get to allocate each of these features into some specific area. These features are represented as PDFs, and we feed this to different 2-level diagnosis using 3-level classifiers to get local and global diagnosis. The crucial step here is the segmentation. Segmentation is a key step for other coming stages. We need to segment each area for each subject to get associated features with this area. Here we adopt an atlas-based segmentation approach, where segmentation is transferred into a registration task. We register each subject brain to a space of atlas. Here we use the Johns Hopkins Atlas. It has 48 different brain areas. And we use the DTI-TK software for registration from this MNI space, atlas space, to each subject area. And for classification, we represent the feature for each area, for each subject as PDFs. We have 500 sample PDFs. Each of these features for each area is fed for first level classifier to get a diagnosis, first diagnosis probability, the diagnosis of being autistic or not. This probability, this posterior probability for each area, for each feature, is then fed to another second layer classifier, which gives us a probability of this area being associated with autism or typically developed person. This probability we have for each area here can represent a correlation between autism and these different areas, and we use this as a personalized correlation maps. And after the last stage classifiers based on these probabilities, we have a global decision. similar to what we did on DTI. The structural MRI pipeline is presented here. But for pre-processing and segmentation, we use free surfer. And we use also Diskin-Kiliani Atlas for brain parcellation. It consists of 68 areas. We extract 8 features for the structural MRI. We extract 8 features representing volumetric and morphological features. And also it's fed to another two-stage classifier, but based here on forced classifier, not SVM. And for the fMRI can be divided into, there are 2 types of MRI. The first type is task-based fMRI, where the patient is asked to do a task, and we get the association of activated brain areas with this task. And there is another type which is resting state fMRI, where the patient doesn't do anything, and we record the normal activation during resting. This is has an advantage for early stage for infants that it doesn't require any collaboration with the child. So we use resting state fMRI in this part. So we feed this fMRI 40 data. We pre-process it using another software, FSF, and we also use Diskin-Kiliani Atlas for parcellation. We get activation function for each area, and we measure the connectivity, the function connectivity between each area and other areas, and to get the function connectivity analysis. These correlations are fed to the another two-stage classification system that also provide us with correlation between each of those correlated areas and autism, and also a global classification for each subject being autistic or not. The participants in our study are from National Database of Autism Research database. We have 185 subjects for SMRI and fMRI data, and we have 172 subjects for DTI data. And on common, which used for fusion, we have 137 subjects. We tested them for gender and age differences, and it was found between the 2 groups that are not statistically significant. And using this framework, we achieve the accuracy of 81% after fusion. Each modality alone achieved 70s, a series of 70s. We also not only provide high global accuracy, we have here the local association between brain areas and autism included as a color map. This color map, if it's blue, it represents that the person is more associated, this area is more associated with typically developed persons, and red is more associated with autism phenotype. And in this column have autistic subject, and this is typically developed, and the same here. This is for SMRI and fMRI, and this is for TI. And of course, we see that autistic people have more red areas here than developed persons. Using this color maps, it can help to get a personalized diagnosis that really aids the patients. So in conclusion, this work proposed our CAD system that made to use morphological SMRI data and connectivity information. And this analysis would help to allocate the subject on the autism spectrum, not only providing whether he is autistic or not, it also indicates which areas are affected with this person in terms of functional or connectivity. This may help clinicians to deliver a personalized treatment for individuals. And thank you. Question?
So based on what you said, like based on what you try to integrate, like 3 modalities. So what, from your opinion, what is the extra information you can get from DTI or from structural MRI or functional MRI?
Each of these modalities gives us different information than other modalities. For example, functional MRI gives us the activation of for here in resting state, the activated brain areas. While in resting, there is some theories, for example, that autistic people has more isolated brain areas, so they are not activated in the same time. And for example, for white matter, we can get connectivity between all brain areas or inside each brain area. So it gives us other information about the white matter area connectivity, the pathways in normal case. So the autism spectrum, there are different types of autism. So like if we can get these different types of information, and we can see all the spectrum of autism. So one autism spectrum may be more prominent in structure. It can be detected by structural information, but not from functional information. And integrating this all together can help us to get better diagnosis. Yeah.
Okay. I have 2 questions. Okay. First question is that what is your age group, the sample
Sample size?
Yeah, sample size and the age group of the
age?
Yeah.
Yes. The age group here we tested we range from 8 years to 17 years, as we. The age range from 96 months to 250 months. This is from what 8 years to 17 years.
Okay. And you said that you divide the brain into area, right?
Yeah.
How did you decide this? How did you separate this area?
Yeah. So I went through this first. We used the atlas. There is a predefined atlas. It's used from 81 different subjects. It's hand segmented, and this atlas base has labels for each area, and we register our data, our brain, our MRI data, for example, volume. We register to this atlas space, and we can get labels for each area.
So which brain area we should focus on to find what is wrong? What do you think? Because it is a very complex thing, okay?
Yeah.
No.
According to, I don't have the results here. According to our work, we have like for functional, we detected 5.
Yes, so
Yeah,
for this, for the functional and for the structural and what we are currently doing in the DTI, in addition to the classification work, we have also studied the correlations with what's called ADOS report, ADOS diagnosis observation schedules. And we have detected some neurocircuits in the functional MRI, for example, that showed high correlation between decreased or increased functional connectivity between a couple of areas and such ADOS reports. So these areas were defined by our medical collaborator from the Autism Center at UofL, and they were found most likely to be correlated with language behaviors and with restricted repetitive behaviors. I'm not familiar with such anatomy, but they are mainly near the frontal loop. There are many areas near the frontal loop, but this could be shown also here in such color-coded maps. The areas that showed in many subjects.
Can you find color? Which areas are?
Thank you. Well, that's all we have time for questions.
Okay. Okay.
So the areas that
Yeah,
showed.
please meet afterwards to continue your discussion.
Okay.
We're running a slight bit behind. So keep on going. Our next speaker is Mohammed Shahata from the University of Louisville. He's going to present some of his work on early assessment of acute renal rejection post-transplantation, a combined imaging and clinical biomarkers approach or protocol.
Make sure that everything is working. And I know where.
So, good afternoon, everybody. My name is Mohammed Shahata, I'm PhD student in the Computer Science Department and Graduate Research Assistant with the Bioengineering Department. Today's talk will be about early assessment of acute renal transplant rejection, and it's a combined imaging and clinical protocol. First of all, I'm going to talk about the problem and the unmet need. Chronic kidney disease is considered as the 9th leading cause of death in the United States and the 12th worldwide. And 50% of population in the United States are suffering from chronic kidney disease. Actually, the definitive therapy for the end-stage chronic kidney disease is either going to through the dialysis or the transplantation. And the definitive therapy for that is transplantation. In the USA, 2014 and 2016, there were around like 117,000 patients waiting for renal transplants. However, due to the dearth of donors, only 17,000 were performed. 15% of acute kidney transplant rejection are diagnosed with acute renal rejection during the first 5 years. So, all efforts should be employed to maintain the survival, to prolong the survival rate of the kidney transplant. What I'm talking about here, after kidney transplantation, if the rejection of the kidney hadn't been detected at the early stage, the kidney function will worsen, and then the symptoms will arise, and then leading to a kidney failure again, which we will not need. In our system, we are targeting this area, the early detection. First of all, I'm going to talk about the current diagnostic techniques and their limitation. Most of the clinical research are diagnosing the kidney rejection based on the GFR, which is the glomerular filtration rate. Basically, the glomerular filtration rate is based on the creatinine clearance and the plasma creatinine indices, and they are not precise and are later markers because like the change in the GFR amount is only detectable after the 60% loss of the kidney function. So after, based on the GFR, the clinicians recommend the biopsy, and they are going through the biopsy procedure to take some sample tissues from the transplanted kidney, and they start to see if it's rejection or non-rejection. However, it has significant cost based on initial estimation at the University of Global Hospital from our medical corporation, Ahmed Wire. It costs around 22,000 for the biopsy, and it's invasive as well and has morbidity rates. Also, it may over or underestimate the problem of sampling areas, so maybe has some errors as well, and the complications, it has some bleeding and infection and even death. So our research objective here to have an early diagnosis of acute renal transplant rejection, and to be in a non-invasive way, and at an early stage, so that we can prolong the survival rate of the transplanted organ. Talking about the non-invasive techniques that are currently used, they are mainly based on the imaging techniques. Some of them are based on using the computed tomography images and scintigraphy or radionuclide. However, they have some radiation exposures, and some of them are using the MRI modalities. Some of the MRI modalities that has been previously used, the dynamic contrast enhanced MRIs, diffusion weighted MRIs, and bold MRIs. However, dynamic contrast enhanced MRIs are basically based on the using the contrast agent, which may lead to nephrotic system fibrosis for these patients. So, in our study, we are selecting diffusion weighted MRIs because they are suitable for all kinds of patients. I mean, all kinds of patients, the patients that have GFR or glomerular filtration rate greater than 30 milliliter per minute or lower than 30 milliliter per minute. And they are providing also anatomical and functional information about the kidney. Here's like a simple framework about the developed computer-aided diagnostic system. Actually, what's been new here that we are collecting data from different locations, from different centers. We have data from Egypt, Mansoura University Center. We have data from University of Michigan. And we have also data from different Tesla scanners. So we have a GE scanner, which is 1.5 Tesla, and we have Philips scanner, which is 3 Tesla. We are collecting 4D diffusion weighted MRI. I mean by 4D, 3D, like the whole volume of the entire kidney to cover all the cross section to cover the whole of the entire kidney volume. And the fourth dimension is the gradient, which is changing the gradient field and the duration during the acquisition of the other marker, as I said, because like it's a combined protocol between the clinical and the image markers, we are collecting the creatinine clearance based on the urine test and the serum creatinine or serum plasma creatinine based on the blood test. The first step is to segment the kidney to provide an accurate estimation of the functional parameter later on. So we have to extract the organ of interest. The organ of interest is the kidney, and when we acquire the DWMRI images, we have some other surrounding tissues. So the first step is to provide an accurate segmentation of the kidney. We are making the kidney segmentation using the joint MGRF, which based on combining three models. The first model based on the intensity, the other one the spatial interaction between each voxel and the 26 neighborhood, and the third one is a probabilistic shape model, which is based on the manual segmentation or ground truth. After that, we have the 3D segmentation final results. I'm showing you here some results for coronal, axial, sagittal, where the green contour here is the model segmentation, which is the ground truth by a board-certified radiologist, an MR expert. And the red here is our model segmentation. And more results about this has been published in the journal PLOS ONE. The second one, the second step, going back to the framework, is to start extracting the diffusion parameter. Actually, the common parameter in the diffusion with MRI images is called apparent diffusion coefficients, and it depends on the motion of the water molecules inside the soft tissue that we can quantify the amount of diffusion. So to extract this, it is like we have 12 B-value scans. The baseline, has no diffusion, and this is like the 3D representation of the entire kidney volume. For example, if we need to calculate the apparent diffusion coefficient at the B500, this is the entire 3D kidney volume for the same cross section. And then we use the equation defined by Lebehan ADC, where the G is the signal intensity or the gray level of the voxel, of the entire voxel, divided by the G0, which is the same as the gray level for the same voxel at the baseline. We get a 3D voxel ADC maps. The third one is the integration process. Here we need to integrate the clinical biomarkers for every patient we have with the image markers. So we have integrated that. We can see here the representation or the mapping of the apparent diffusion coefficients through what's called CDFs. The CDFs is the cumulative distribution function. We are accumulating the probability distribution function along 100 regions. These 100 regions are specified based on the maximum ADC value, the minimum ADC value, and the minimum increment we have. And then when we build up the clinical biomarkers or augment the clinical biomarkers with the image markers, we have these nice CDFs for the two groups, the non-rejection group and the acute rejection group. This is just showing a sample of 6 patients from each group. Basically, we have 56 subjects, where 38 are males and 18 are females. The age range between 12 and 65. And the number of p-values we have are 12, from B50 to P1000, and we have the baseline. 26 are non-rejection and 30 are acute rejection. 34 patients were collected from Egypt with a 1.5 Tesla GE scanner, and five patients were collected also from Egypt to 3 Tesla scanner, and 17 patients were collected from the University of Michigan with Tesla scanner. The last step is the classification. So after getting these new features called integrated ADCs, which integrate both the clinical biomarkers with the imaging markers, we started making the classification step based on the leave one subject out approach. So here I'm showing the results for the imaging markers alone in terms of accuracy, sensitivity, and specificity, and the clinical biomarkers alone in terms of the same metrics. And then when we fuse both the biomarkers together, we have an enhanced diagnostic accuracy here, and sensitivity and specificity. Also, I have tried several classifiers. I have tried the autoencoders based on the neural networks. I have tried the KNN, nearest neighbor, the linear discriminant analysis, support vector machine with linear kernel, and the random forest. And the accuracy is very close. To help the radiologist for the visual assessment as well, we are making color-coded maps for the non-rejection subject and acute rejection subjects as well, which are reflecting the new feature, which is integrated biomarkers between the ADC or the image markers and the clinical biomarkers, and it's visually different. To summarize, the proposed CAD system for early detection of acute renal transplant rejection has a high diagnostic accuracy of 93%. The fact that the distinguished non-rejection and the acute rejection subject was achieved with the integrated clinical and imaging markers suggested that a major advance of our method is the integration of personalized data for this medical condition. We have a granted patent on that with Dr. Baz. It's recently, and we have support grant like the NIH, the Culture Internet Grant Phase 2 Extended, the joint grant between us and Egypt, and the Competitive Enhancement Grant. Our future avenues, we are currently running a double-blind test on 10 subjects collected at the University of Louisville and 30 subjects collected at the University of Michigan as well. And we have a preliminary result which is very promising on double-blind test with the University of Michigan on 17 subjects, as we have 88%, 15 out of 17 correct. Additionally, we are collecting genomic data, DNA and RNA sequences in both sides, Egypt and USA, in addition to histopathological microscopic images to investigate the type of rejection, which is the second step for the proper treatment, which can be T-cell or antibody. Another statistical analysis is currently running to investigate the best informative p-values and to see if we can simplify some of these p-values so that we can reduce the acquisition time. Thank you so much.
I think we have time for one question, if anyone from the audience has one.
Okay, so good presentation, I like it. I see that you count here and just using linear model to estimate the ADC. Do you have any plan to find a parametric model that you can use it to what is called combine all the p-values and start to estimate some information about it that can capture or discriminate accepted kidney from rejected kidney?
Yeah, actually we are running right now a statistical analysis to trying to fitting the model with all the p-values starting from B50 to P1000 and trying to make two different models, which is nonlinear models, which can capture any value of the ADC at any p-value. The first value will go from the, would account for the low p-values going from B50, B10, 20, 30, 40, 50, 100, and 200. especially to account for the blood perfusion, and the other model will account for the water diffusion for the high B values considered from 300 to P1000. So yeah, we are currently running as this can answer that.
Thank you.
Thank you so much.
Our next presenter is Fatma El Zahra El Gamal from Mansoura University, and she will be presenting on a significant regional-based diagnosis system for early detection of Alzheimer's disease using SMRI scans.
Good afternoon, everyone. My name is Fatma Zahra, and I'm here today to present a part of our project that deals with the early diagnosis of Alzheimer's disease. And our work today is, or the paper today is under the title of A Significant Regional-Based Diagnosis System for Early Detection of Alzheimer's Disease Using Structural MRI Scans. The outline of the presentation today will go through background, motivation, related work and contribution, proposed framework, experimental results, conclusion, and future work. Starting with the background, Alzheimer's disease is considered as one of the main neurodegenerative diseases that affect the central nervous system, as well as it's considered as one of the leading causes of dementia, where it represents 60 to 70% of the dementia cases in elderly people. According to a statistical report that have been shown in 2016 through the Alzheimer's Disease International Alzheimer's Disease International Organization, 44 million people around the world have been found to suffer from Alzheimer's disease, from dementia-related disorders, including Alzheimer's disease, where 1 in 4 sufferers of AD has been diagnosed. And according to the same report, this number is exposed to be massively increased in 2050 to around 131 million people around the world due to the rapid growth of the aged population. Due to the clinical symptoms as well as the pathological features of the disease, and according to the literature, the disease goes through 3 main stages, which are the early or mild stage, intermediate or moderate, and late or severe stage. Actually, different tests can help in the can assist in the diagnosis process of the disease, including the brain biomarkers, due to their significant impact in this context. According to a study that have been published in 2010, and that address the role of each of the brain biomarkers along the disease cascade, this study found the role, different roles of different brain biomarkers during the disease cascade. Among these tests, we can find the brain structures represented in the form of the structural MRI, and we can see here it's the role of the structural MRI in the mild cognitive impairment stage, which is the early stage of the disease. That's why, when our work, we use the SMRI technology to present our diagnosis system. Several diseases have been emerged to help in the diagnosis of the Alzheimer's disease, but the problem is these works either address the diagnosis of the brain as a whole, they are just classifying the subject as belonging to the normal control or the diseased group, or they address the local or regional diagnosis. I'm sorry, I just forget to mention that the early stage of the disease, I mean diagnosing the disease at its early stage, is considered as the main obstacle that faces the researchers who are working in this research area due to a number of factors, including the variability of the disease among its sufferers. Returning to the related work, as I said, they either address the diagnosis of the brain as a whole, or they address or proposed a local or regional-based diagnosis system, but without dealing with the mild cognitive impairment stage, which is the early stage of the disease. So that's why our contribution is to present a computer-aided diagnosis system that helps in the early diagnosis of Alzheimer's disease, but the main contribution is to present a local-based or local or regional-based diagnosis of the disease, that rather than working with the brain as a whole, we are working with the locally with the brain regions. Besides this contribution, we also aim to improve the overall performance of the system as validated with the related work. To achieve aforementioned goals, our system goes through a 5-stage pre-processing, brain labeling, feature extraction, statistical analysis, and diagnosis. Starting with the pre-processing step, the goal of this process, the main goal of this process is to standardize the brain scans in order to allow the brain labeling process to achieve the main goal of the paper, which is providing a local original based diagnosis of the disease. Beside this goal, we also aim to, we also strip the scalp from the brain scans. So the pre-processing steps will start with skull stripping operation, utilizing the mask of the SMRI scans. Then we will standardize the brain scans to match the labeling atlas template space through reorienting, realigning, spatially normalizing, and reslicing the scans. So at the end of this process, we will have a structural MRI of the tested groups that match the template space of the labeling atlas. Then in the next step, we will perform the brain labeling process, which that will help in achieving the main goal of the paper, which is presenting a local original based diagnosis of the disease. So the goal of this step is to parcellate the scans to the corresponding anatomical regions. And in order to achieve this step, any of the detailed brain regions atlases can be used. In our work, we used automatic anatomical labeling atlas due to its role in providing a fine detail of the brain that's represented in defining 116 different brain regions. So at the end of this step, each of the brain of the subject MRI scans will gonna be parcellated to 116 different brain regions. The next step is to extract the discriminant feature that can help us to differentiate between the tested groups, and to achieve or to perform this task, and relying on the nature of the disease as well as the utilized modality, which is the structural MRI, 2 geometric features have been used, which are the bounding box that calculate the smallest rectangle around each of the segmented or labeled brain regions, as well as the perimeter, which calculate the distance between around the boundary of each region through calculating the distance between each pair of pixels in the boundary of the region. And after obtaining these 2 features, and in order to present or to provide more informative and representative feature vectors, we performed a feature fusion between these 2 features. After this step, and before going to the diagnosis process, we performed a statistical analysis step. The aim of this step is to determine the most significantly affected brain regions to work with them in the diagnosis process, rather than working with the whole 116 region. So to provide more precise and good performance results. To achieve this goal, we used, because we have 2 classes, normal control and mild cognitive impairment group, we used 2 sample t-tests with Benfroni method, where the region is considered significant when its p-value is less than 0.05 divided by 160, which is the total number of the brain regions. The last step of the proposed framework is the diagnosis step. Actually, this step, it's partitioned into 2 different levels. The first level provide the main contribution of the paper, which is the local diagnosis, original diagnosis. In this step, the features of each of the significant regions will gonna be used to construct a separate classifier, and the output of this classifier will gonna be the severity of the disease in this region separately. For example, if we have, and as we will see, we got 19 significant regions, so we will have 19 classifiers at the first level, and actually we used here probabilistic support vector machine in order to reveal the severity of the disease in each of the significant regions. After finishing this level of diagnosis, which achieved the main contribution of the paper, we concatenate all these local results and input them to a final standard support vector machine in order to present the final subject-based diagnosis. I just want to mention here that the first level produce original-based diagnosis, while the second one present subject-based diagnosis. To evaluate our system, we used a total number of 147 scans of 60 normal control and 87 mild cognitive impairment from a standard database called ADNI database, which is a standard database that's used in this research area. The evaluation process went through two main processes. The first one is to evaluate the statistical analysis results, while the second level of evaluation deals with evaluating the diagnosis performance through comparing the performance of using all the 116 regions versus using just the obtained significant regions, and comparing the classification performance of the used classifier against some of the state-of-the-art classifiers, and at the end validating the obtained system's performance with respect to the related work. Starting with the statistical analysis result, as I mentioned before, we got 19 different significant regions, and according to the literature, we could find the relation between Alzheimer's disease, or the effect of the Alzheimer's disease on these regions. Then we, to evaluate how these regions can help in the performance, we compared the results of using just significant regions against using all the brain regions, as we can see here in the table. Actually, according to the table, we can see similar results. Yeah, we can find that using all brain regions can have tiny better results than using just the significant regions, but this still shows promising results of our system, since rather than working with all the 160 regions, we just worked with 19 regions and could achieve this high performance results. Then comparing our classifier with other state-of-the-art methods, we found that our classifier achieved better results, and at the end, validating our system with some of the related work, we found that we have promising results since, for example, the first related work, they achieved accuracy, specificity, and sensitivity of 85%, 80%, and 87%. And at the end, I just want to give an example of our main purpose of the paper, which is providing local or regional diagnosis of the disease. Here we have two groups, normal control and MCI, with two different subjects in each of these groups. And these colors indicate the severity of the disease in each of the significant regions, where the color purple indicate the MCI level, with the 0 indicate the unaffected region, and the black indicate the existence of MCI, the total indication of MCI in this region. As a conclusion, we propose a significant local or regional based diagnosis system to help in the early diagnosis of Alzheimer's disease, where the promising results encourage the authors to evaluate the system with other datasets, as well as continue analyzing other brain biomarkers in order to assist in the early diagnosis process. Thank you.
I believe we have time for one question. So the scale, so that lets you say not only for Alzheimer's, but the severity of the progression? Is that? Okay, so to your knowledge, can doctors use that to change a treatment option? Or, I mean, does that change how the disease is addressed to know this? Or?
Yeah, actually, this can help too, because as I said before, the variability of the disease affecting each of the brain regions, I mean, determining the severity of the disease in each of the regions means the affected function of this region. For example, if I have the region that is responsible for the memory, so that this can help in the treatment process to use therapies or treatment medication that can help them keep the daily functionality of the memory function of the patients, and that's it. So yeah, determining the severity of the disease in each region will help in the treatment process to determine the suitable medication for each of the affected brain regions. Mm-hmm.
Thank you. Our final presentation of the morning session will be presented by Zaviha Auger. It's automated staging of diabetic retinopathy using a 2D convolutional neural network.
Hi everyone, I'm Zaviha Auger. I'm a master's student in the University of London, and I'm here present the paper automated staging of diabetic retinopathy using a 2D convolutional neural network. First of all, I will start with talking about what is retina. Retina is the layer in the back of the eye that triggers the electrical impulses to reach optic nerve, then to the brain to form the image. And the retina is composed of the three types of nerve cells and 12 layers of and 12 different layers. And there are three common retinal diseases, which are diabetic retinopathy, macular degeneration, and hemorrhages. And if we want to investigate on the retina, we have three different images, which are fundus photography, fluorescence angiography, and optical coherence tomography, which are called OCT or OCTA. And the main question is, what is the diabetic retinopathy? It is caused by damage to blood vessels in the tissue at the retina, and blood sugar is one of the main risk for this disease. And blurriness, dark areas of vision, and difficulty perceiving the colors, some of the early symptoms of diabetic retinopathy. And unfortunately, at late stages, this damage can cause vision loss. People can be blind after this disease. And thinking about 100 million of U.S. citizens, they already have diabetes, and between 40 to 45% of them already have some degree of diabetic retinopathy, and most of them, they are even not aware of it. And this was one of the main motivation for us to work on this subject. 5 in 100 adults in the United States actually has the DR disease. To do early diagnosis of diabetic DR disease, as well as the other retinal diseases, we have some of different data to use, and these are clinical data, genome, demographic data, and imaging markers. And we use this part, especially the promising results, what the previous work have done about that subject, and it includes OCT, OCTA, and fundus images. Our work is focused on fundus images. And the ultimate goal of our work is create an objective automated technology for diagnosis of DR disease to improve the patient outcomes and avoid the unnecessary treatment. And to achieve this goal, we want to develop a CNN-based CAD system to detect the DR disease, classify and stage a subject into one of the 4 main classes of DR, and without any pre-processing steps. This is our architecture of our proposed CNN work, and it is we get the input, then our input is 3D images, 3D fundus images, and we took them through 2D convolutional layer to extract the features, then pooling layer to reduce the parameters, and by unsampling, subsampling, and after that we use the softmax layer to calculate the cross entropy loss to achieve our goal. Our data collection step was, especially in this paper, 101 fundus images we have used, and these were included from 4 different classes of DR. These are normal retinas, mild, moderate, non-proliferative diabetic retinopathy, which called NPDR, and severe NPDR, and proliferative diabetic retinopathy, which called PDR. And each class has 25 fundus images, except the first class. It has 26. And our experimental result is we split our data to 4 batches, and each batch has 25 samples, and we trained our network with 35 epochs and 50 epochs to see the influence of epochs to performance. And we use for testing leave one subject out cross-validation, and we repeated these steps 101 times. And this shows actually increasing the epochs has help us to improve the accuracy, as we see here. With training, our result was almost the same with 35 epochs and 50 epochs, but when we see the testing accuracy, we have 4 percentage of increasing, as that 50 epochs was 80%. Conclusion and future direction. In the current study, we propose a 2D combinational neural network was introduced to detect and classify DR subject into normal, MPDR, severe MPDR, and PDR. A dataset of 100 fundus images were trained using the proposed network, and leave one subject out cross-validation was used for testing the network. A testing accuracy of 80%, almost 80% was achieved, and training accuracy was almost 100%. With the obtained promising results, we think that specialists can use the automatic computer-assisted diagnosis tool that deploys the CNN to sufficiently diagnose and classify subjects without the need for traditional subjective physical assessment that may lack sensitivity or precision. And this was my presentation. Thank you so much.
We do have time for a question. So you said you have a testing accuracy of 80.2, training accuracy of 99.9. What was your ground truth? So how do you know? So you're looking at accuracy. So what does it compare to? So how do you know if you say class 1 or class 2, that it was indeed class 1 or indeed class 2? What is your ground truth on which you're basing that accuracy on?
I mean, we have the 4 classes, and
so do you have specialists
doctor
that
doctor report, yeah, doctor report about this, he classified. The data comes with a doctor report that have every class.
All of these data are labeled by an expert.
they were already labeled which class we had already.
And then you conclude that your proposal can classify subjects without the need. Is it based on the 80.2 or 99.9?
80.2.
Right? And so how can you further improve that?
We are thinking to use more data for improvement, but so far we are going to try to use for more data to have better results.
Thank you all. I believe it's lunch break time. One quick thing, happy birthday to my co-moderator.